Today we'll discuss logic. Logic is a formal language that allows us to make assertions about the world in a very precise way. We'll learn about logic both because it is an important topic and also because it forms the basis of additional topics such as planning. We'll start by talking about a formal notation for writing sentences in logic. This formal notation will have things like conjunctions and disjunctions. Then we'll talk about truth tables, a topic that you probably already know. We'll talk about rules of inferences like modus ponens and modus tollens. Finally, we'll discuss methods for proving theorems by refutation. One of those methods is called resolution theorem proving. Let us begin by asking ourselves, why do we need to use formal logic to design an AI agent? The way the formal logic in an AI agent would work is that there will be two parts to the AI agent. The first part will consist of a knowledge base. The knowledge base would contain the agent's knowledge about the world. That knowledge will be represented in the form of sentences in the language of logic. The second part will consist of an inference engine. The inference engine will apply rules of inference to the knowledge that the agent has. So remember again, two parts, the knowledge base and then rules of inference. Now there are certain situations in which we want the AI agent to be able to show, to be able to prove that the answers that it derives to any problem in fact are provably correct. It may want to show this to itself or to other users. In other situations, we may want the AI agent to generate only provably correct solutions. How can we guarantee that? Well, we need two things. First, we need a complete and correct knowledge base. And second, we need rules of inference that will give guarantees of correctness of the answer. The inferencing has two parts to it. The first part is called soundness. The property of soundness means that the rules of inference will derive only those conclusions that are in fact valid. The second property is called completeness. The property of completeness means that the AI agent will derive all the valid conclusions. These are two very important properties to have. If an AI agent can use logical rules of inference on its knowledge base and provide guarantees of soundness and completeness, then that's a very useful thing for an AI agent to have. For this reason, logic has been an important part of AI since the inception of the field. In fact, it continues to be an important part of research on modern AI. In this course, however, we'll discuss logic only to a very limited degree. There are two reasons for this. First, our priorities in this course are a little different. Instead of talking about knowledge in the form of logical sentences, we are much more interested in conceptual knowledge, and experiential knowledge, and heuristic knowledge. Second, recall that we said that a logic-based agent has two parts to it, the knowledge base and the rules of inferences. Even if the rules of inferences are, in fact, guaranteed to be sound and complete, there is a problem about how do we construct a correct and complete knowledge base. If the knowledge base of an AI agent is not correct and complete, then it may not give you useful answers even if the rules of inference are sound and complete. Thus, in this course, we'll use logic only to the degree to which it is useful for specifying other methods that use conceptual knowledge or experiential knowledge or heuristic knowledge. Now, we have come across this particular kind of problem earlier. This was the classification hierarchy. Vertebrates can be of different kinds. Bird is one kind. Birds can be of different kind. Eagle, bluebird, penguin are three classes of birds. Now, an agent may have knowledge like if an animal has feathers, then it is a bird. When we were discussing this classification hierarchy, we had tried to define the concept of bird. And we had said that that time that if an animal has feathers, it is a bird. If an animal lays eggs and it flies, it is a bird. Now, it is sentences like this that we'll try to put in the language of logic. Before we represent those sentences in the language of logic, let us consider another example of conceptual knowledge and its relationship to logic first. So here is the concept of foo. We have come across this earlier. There were a block and a brick at the bottom and a brick at the top, and some relationships between these objects. Given this conceptual knowledge about foo, we can ask ourselves, what are the sufficient conditions for something to be a foo? Here are several choices. Please mark all of those choices that together make for sufficient conditions for the concept of foo. What do you think, David?
So from the bottom, we have that a brick has to support two blocks, not necessarily two bricks. We know that those can be any kind of block. We also have that those two blocks cannot touch. So that condition is important. And we also have that those two blocks must then support a brick. And we learned earlier that it's not sufficient for that to be any kind of block. The block on top has to be a brick as well. So these three conditions are sufficient to define a foo in terms of logic.
That's good, David. So what we are learning here is, given conceptual knowledge, how can we translate it into the language of logic? Recall that we said that a logic-based AI agent will have two parts to it, a knowledge-based and then the rules of inference. We'll come to the rules of inference a little bit later. First, let us look at how can we construct a knowledge base in the language of logic. So what we are trying to do now is that an AI agent has some knowledge about the world and it is going to express it in the scheme of logic. In earlier schemes of knowledge representation, we discussed how there were objects and relationships between objects, and any knowledge representation scheme would need to capture both objects and relationships between those objects. Logic has a particular way of doing it. So consider an object like a bird. This object may have various arguments, and we'll define something called a predicate, which is a function that maps object arguments to either true or false. So let us consider an example. Here we have bluebird as the object and feathers as the predicate on this object. Let's consider this example. Here bluebird is the object and feathers is the predicate on this object. Feathers is now a function that can map either into true or into false. Either bluebird has feathers or bluebird doesn't have feathers. In this particular case, feathers of bluebirds would be true because bluebirds do have feathers. Now just like we had bluebird as the object in the previous example, here we have animal as the object, the same predicate. Now of course not all animals will have feathers, so this particular predicate may be true or false depending on the choice of the animal. In this sentence there are two predicates, one object, animal still, but there is the predicate feathers and the predicate bird. And we can capture a relationship between these two predicates by saying that if feathers animal is true, then bird animal is also true. This example has two predicates. Here there is one object, the animal, but the predicates are feathers and bird, and the sentence is capturing a relationship between the two predicates. If the animal has feathers, then the animal is a bird. In logic, we call sentences like this as having an implication. This is an implicative relationship. So in logic, we'll read this as feathers animal implies bird animal, or if the animal has feathers, then it implies that the animal is a bird. Now consider another sentence that we have come across earlier. If an animal lays eggs and it flies, then it is a bird. How do we write this in the language of logic, given that there is a conjunction here? So this time we can have two predicates again. There is the predicate of lays eggs coming from here, the predicate of flies coming from here, and we can denote a conjunction between them, which in the language of logic is often put in this form. Now we can rewrite this sentence in the following form. If the animal lays eggs and the animal flies, then the animal is a bird. Remember again, this semicolon here really is denoting implication for now. Remember again that in logic, this really stands for an implication. Consider a slightly different sentence. Supposing this sentence was if an animal lays eggs or it flies, then it is a bird. In that case, again, we'll have two predicates, but this time we'll have a disjunction between them. And the sentence would become if animal lays eggs or animal flies, then the animal is a bird. And again, this is an implication. Let us continue with our exercise in which we are learning how to write sentences in the language of logic. Here is another sentence. If an animal flies and is not a bird, so there is a negation here, then it is a bat. How do we write that in logic? So I'm still interested in writing the antecedent of this particular sentence, and I may be able to say that animal flies, there is a conjunction here because there is an and here, and we have this negation symbol for this predicate bird. Now we can write a complete sentence by saying that the animal flies, conjunction, animal is not a bird, implies animal is a bat. Now I have been talking a little bit about implication. Let's see how do we actually write implication in logic. So here is a sentence. If animal lays eggs and animal flies, implication is that the animal is a bird. In logic, we write this using this symbol, arrow symbol, for an implication. So if the animal lays eggs and animal flies, implication, animal is a bird. So here is the left-hand side of the implication, here is the right-hand side of the implication. The left-hand side of the implication implies the right-hand side.
Generally speaking, you won't have these symbols on your keyboard. You can find them in your character map, and you're welcome to use them if you'd like to. But for the exercises in the rest of this lesson and in the next lesson, feel free to use the symbols given over here. These are the symbols for and, not, or, and equals that come from Java or Python. So feel free to use these when you're doing the exercises that you'll come across in the rest of this lesson.
So remember, we are still trying to learn how to build a knowledge base in the language of logic. To put it all together, consider 4 exercises. Here is a sentence. Please put it in the language of logic. Similarly, for this sentence, this sentence, and this sentence. Okay, David, what did you have for the first sentence?
So for the first sentence, I created the predicates lays eggs, feathers, and reptile, and said if the animal lays eggs and the animal does not have feathers, that implies the animal is a reptile. For the second one, I said if the animal has feathers or the animal has talons, that implies that the animal is a bird. So animal feathers or talons, feathers or talons. For the third, which is a longer one, I said if the animal lays eggs and the animal has a beak and the animal flies, all 3 of these all in a chain, that implies the animal is a duck. And similarly for the fourth one, we have 3 predicates on the left side. If the animal lays eggs, the animal has a beak, and the animal does not fly, then the animal is a platypus. This kind of shows us why a platypus is such a strange animal, because we need to make a lot of caveats in order to define what a platypus really is.
Good, David. That looks right to me. So to wrap this part up, let us note that when we defined what a predicate was, we said a predicate like flies can map into true or false. Well, okay, a predicate can map into true or false. What about complicated sentences like this, which have multiple predicates as well as implications? How do we find out whether the sentence as a whole maps into true or false? That's what we're going to look at next. We're looking at truth tables. So we'll now build truth tables for conjunctions and disjunctions and negations of sentences so that we can find the truth of complex sentences stated in logic. Now, many of you probably are familiar with truth tables, and if you are in fact familiar with truth tables, then you can skip this part and go directly to implication elimination. If you're not familiar with this, then please stay with me, but even so, I'm going to go through this quite rapidly. So here is the truth table for A or B. If A is true, then B. If A is true and B is true, then A or B is true. If A is true and B is false, then A or B is still true because A was true. If A is false and B is true, then A or B is true because B was true. One of them is true makes this true. If A is false and B is false, then A or B is false. Let us try a couple of simple exercises. So here we have A, B, and we want to find the truth value of A or not B. Given these values for A and B, can you please write down the truth values for A or not B? And similarly for not A and not B. David, what did you get?
So for A or not B, I got that if A is ever true, then this has to be true because it's A or not B. When A is false, the negation flips the value of B, so it makes it true when B is false, but keeps it false when B is true. For not A and not B, that means that anytime either A or B is true, then this is all false. So when A is true, this is false. When B is true, this is false. When both are false, this becomes true because those negations flip the values of both A and B.
Now we can play the same game for ever more complex sentences. So here are again 3 predicates A, B, and C. And here's a more complicated sentence that involves all 3 of those predicates. A or B, and within parentheses, B and not C. And we can find the truth values for this particular sentence given the truth values for the predicates A, B, and C. Why did you give it a try and write down the values here? David, what did you come up with?
From the beginning, we start with A or something. So as long as A is true, then we know the result is true. We don't even care about the rest of it. When A is false, then we need to look at B and not C. Because this is an and, we need both B and not C to both be true. So when B is false, we can go ahead and say this is false over here. And when not C is false, we can go ahead and say that this is false over here. Not C is false if C is true, so this is also false. So our only other answer that's true is that row right there.
So as you can see, this can become very complicated very quickly. But David did get the answer to the truth value of this particular sentence based on the truth values of the predicates that are inside the sentences. So in principle now, we can see how we can compute the truth value of very, very complicated sentences written in logic. The construction of these truth tables allows us to illustrate certain important properties of logical predicates. To see those properties, let us do an exercise together. So here we have the predicate A and the predicate B, and here we have A and B and A. Please fill in these boxes the truth values of A and B and the truth values of B and A. David, did you fill out the boxes?
I did, and I got that whenever either of them is false, we see A and B as false. It's only true when they're both true. B and A is the same thing as A and B, and we can see that because the truth values for B and A come out as the same as A and B.
That's good, David. And as you know, this property is called the commutative property. The commutative property says that the truth value of A and B is the same as the truth value of B and A. So whenever I have A and B, I can rewrite it as B and A. Let us try a slightly more complicated exercise. This time we have three variables, A, B, and C. And here are the combinations of the truth values of A, B, and C. Here on the right are two formulas. The first one says A and parentheses B or C, parenthesis closed. The second says parentheses A and B, parenthesis closed, or parentheses A and C, parenthesis closed. Please write down the truth values for these two formulas. Did you write down the truth values for these two formulas, David?
I did, and on the one on the left, we find it's a little bit easier because it starts with A and, which means anytime A is false, we can go ahead and write that this is false. When A is true, that means we can ignore it and evaluate solely based on B or C. Whenever either of them is true, the result is true, and only when both of them are false is the result false. So the one on the right is a little bit more complicated because for each of them, we need to look at both A and B and A and C. But because there's an or in the middle, that means once we discover that one of them is true, we don't need to really worry about the other one. A and B is true whenever both A and B are true, and so A and B are true here and here, meaning we can go ahead and say that those are true. We don't need to look at A and C here. Similarly, A and C are true here, so we can go ahead and say that this one is true as well. For all the ones at the bottom, A is false, which means it's going to go ahead and render both of them false. And for the fourth one, B and C are both false, meaning each individually is going to become false. So what we see here is that the truth values for these two formulas actually end up the same, so I guess they're equivalent as well.
Good, David. So this property is called the distributive property. The distributive property says that these two formulas have the same truth values, and in particular, if there is B and C inside the parentheses with a disjunction between them, and A is outside the parentheses with a conjunction between them, then we can move A inside the parentheses by first writing A and B, and then writing A and C, and taking the disjunction of the two.
We can also think of this as distributing the part outside both the predicate and the operator into both the ones on the inside. We take the A and apply it to B, so A and B. We take the A and apply it to C, so A and C. And we preserve the operator in between B and C, in between the two new parentheses. So if this had been A or B or C, this would become A or B or C. If this had become A and B and C, and would be all the operators here.
Let us do one other exercise in truth tables to illustrate one other property of logical predicates. Again, here are three predicates and here are two formulas. This should be a simple exercise. Please write down the truth values of the two formulas in these boxes. What did you get, David?
So like before, because this is an or, as soon as we see that A is true, we can go ahead and write down true for all of these. When A is false, we just need to evaluate B or C. When B is true, we know it's already true. And then if B is false, we need to look at C. If C is true, then it's still true. And if C is false, then all three are false, and that's the only time it's false. Over here, we've moved the parentheses, but really we're not changing what we do. We can think of it as starting at the bottom with C being true. Anytime C is true, the entire thing is true. So C is true here, 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 and here. If that evaluates the false, we need to look at A or B, and so on. So we end up doing the exact same process.
That's good, David, and this property is called the associative property. The associative property simply says that we can change the location of the parentheses here, A or parentheses B or C, parentheses closed. It has the same value as A or B, parentheses closed, or C, so that we can change the location of the parentheses. The same would have been true if these were both conjunctions. If it was A conjunction parentheses B conjunction C, or A conjunction B conjunction C, it would have had the same values.
The difference between these formulas and the ones we were doing before are the values of these operators. Associative property works when it's both ors or both ands. Distributive property worked when there was a mixture of operators.
One other property of logical predicates that we will see very soon in action is called the De Morgan's law. So this time there are two predicates, A and B. Here are the truth values. And here are two formulas. Remember, this is a negation. Please write down the truth values of these two formulas in these boxes. What did you get, David?
So for not A and B, we just take the value of A and B and flip it. A and B is only true when both are true. So when both are true, this becomes false. And any other time, this becomes true. Not A or not B becomes true whenever either of them are false, because the false value will be flipped by that negation, and that's all that'll matter because this is an or. So we see A is false here and here, B is false here, so those are all true. When they're both true, this becomes false because both those truth values are flipped.
That's good, David. So the De Morgan's law is saying that when we try to distribute the negation over the predicates inside the parentheses that are connected with a conjunction, then the conjunction becomes a disjunction between the negations of the predicates. The same would have been true if we had a disjunction here. When we distribute the negation, it would have become a conjunction here. David, before we go ahead further, let's remember why we are trying to do all of this. So recall we said in the beginning of the lesson that a logical agent will have a knowledge base and then formal rules of inference that will apply on the sentences of the knowledge base. The knowledge base itself may be coming from many places. Some sentences in the knowledge base may be bootstrapped into the logical agent. Other sentences may be coming from perception. Now, when we are trying to apply these rules of inferences to the sentences in the knowledge base, it is sometimes very useful to rewrite these sentences in different forms. And that's what we are trying to do. These properties will allow us to rewrite these sentences in such a way that we can in fact apply the rules of inferences that we will see in a minute. Recall that we had said earlier that if we know the truth values of various predicates in a sentence, then we can compute the truth value of the sentence as a whole. Well, a sentence may contain an implication. So that raises the question, how can we compute the truth value of an implication? This table gives us the truth value of implications. A and B are predicates, and here is A implies B. To see the truth value of A and B, note that when A is true and B is true, then we understand A implies B is true. This is as usual. When A is true and B is false, this implication cannot be true. So this is false. And if A is false, then it doesn't matter whether B is true or false. This implication will be trivially true.
So it can be a little bit weird to talk about the truth value of an implication sentence. What we're really saying here is whether or not this implication actually holds true. So let's take 3 different implications to see this. First, let's think of the implication, feathers implies bird. All birds have feathers, and only birds have feathers, so we know that if an animal has feathers, then it is a bird. That's true. On the other hand, let's take the implication, if scales, then bird. Lots of animals with scales aren't birds, and in fact, no animals with scales are birds, so the implication, scales implies birds, would be false. For a third example, let's take the implication, flight implies bird. If we have a penguin, flight is false. But the penguin is still a bird, so flight can be false and bird can still be true, meaning the implication can still be true here. On the other hand, if we have a cat, flight is false and bird is false, so the implication can still be true. So in this case, if flight was false, we can't actually make a determination on whether or not the animal is a bird.
As we go ahead and start applying rules of inferences to sentences in a knowledge base, we'll find it convenient to rewrite these sentences in the knowledge base. And sometimes it will be very useful to rewrite these sentences in knowledge base in a manner that eliminates the implications in a sentence. And this is how we can eliminate the implication. If A implies B, then we can rewrite it as not A or B. We know this because the truth value of A implies B is exactly the same as the truth value of not A or B. We can take an example here. Supposing that we're given feathers imply bird, then we can rewrite this as not feathers or bird. And intuitively you can see the truth value of this. It is either that the animal does not have feathers or it is a bird. In a little bit we will see that this is an important rewrite rule in doing certain kinds of logical proofs. Okay, now that we have looked at how to write sentences in the language of logic and also looked at how to rewrite these sentences, for example, by eliminating implication, let us now look at what kinds of rules of inference can we apply and how can we apply them. One rule of inference is called modus ponens, and many of you may already be familiar with it. If I'm given a sentence S1 which says P implies Q and another sentence S2 which says P, then I can infer Q from it. P implies Q and P, therefore Q. This symbol stands for therefore. Let's take an example. So imagine that I'm given that feathers imply bird, and I'm also given that feathers is true. Then I can infer that bird must be true. Now we can connect this to a logic agent. Imagine that there is a robot, and I bootstrap that robot with the knowledge that feathers imply bird. Now the robot goes to a new region in the country and finds some animal which has feathers. The robot can now conclude that that particular animal is a bird. So the first sentence came from something that I had bootstrapped into the knowledge of the robot. The second sentence came from the percepts of the robot, and the third sentence came from its logical inferencing. And this is how the robot can in fact go about making sound, complete inferences that are guaranteed to be correct. Here is a second rule of inference. This is called modus tollens. So again, I have sentence S1, P implies Q, and I have a second sentence, not Q, and therefore I can inference that not P. So let us take an example of modus tollens. Imagine that there is a robot that has been programmed, bootstrapped with the knowledge feathers imply bird. So that's part of its knowledge base already. This robot goes to a new country and is talking to the people in that country, and the people tell the robot a story about an animal that is not a bird. Therefore, the robot may infer that that animal must not have feathers. So this is coming from the knowledge that is bootstrapped. This is coming from the new percept from the story, and this is coming from the logical inference. And once again, the logical inference is guaranteed to be sound and complete.
You may already be familiar with this line of reasoning because this is another way of phrasing the contrapositive that we see in other areas of logic.
Now you can see how we can apply these rules of inferences on sentences in a knowledge base of a logical agent to prove all kinds of sentences. So imagine that an AI agent begins with the knowledge that if an animal has feathers, it implies that the animal is a bird. Now it comes across Harry, who does have feathers. By modus ponens, therefore, the AI agent can conclude that Harry is a bird. This completes the proof for our original goal of proving that Harry is a bird. Now let us suppose that the goal is to prove that Buzz does not have feathers. Once again, imagine an AI agent which begins with the knowledge that if an animal has feathers, it implies that the animal is a bird. The AI agent comes across an animal which is not a bird. Then by modus tollens, it can infer that Buzz must not have feathers. This completes the proof for our original goal of proving that Buzz does not have feathers. Okay, so now we have looked at two ways of proving the truth value of various sentences. The first way was just through truth tables. I could have sentences in logic, then I could write another sentence and ask myself, well, what is the truth value of this sentence? I could construct a truth table for that sentence composed of the truth values of all the predicates, some of which might be coming from earlier sentences. The second way in which we have seen how we can prove the truth value of sentences in logic is by applying these rules of inferences like modus ponens and modus tollens. This is very powerful, and in fact the power of this logic has been known since before the birth of AI. As computer scientists, however, we'll analyze this power in a slightly different way. Yes, we can use the method of truth tables to construct the truth table for any arbitrary sentence. However, if the sentence was complicated, then the truth table very soon will become very complex. Computationally, that is infeasible for very long, large sentences. Similarly, yes, we can apply simply modus ponens and modus tollens to find the truth value of many sentences. But if the knowledge base consisted of a very large number of sentences instead of just one or two sentences, then the kinds of inferences, the number of inferences I can draw from those sentences simply by applying modus ponens and modus tollens will be very large. Or if I had to find the truth value of a single sentence, then the different pathways I could take in order to get to the truth value of those sentences can make for a long, large problem space. So while these methods of proving the truth value of sentences in logic have been around for a long time, these methods are not computationally feasible, at least not for complex tasks, at least not for agents that have only limited computational resources and from whom we want near real-time performance. Before we show you a computationally more feasible way of proving theorems in logic or proving the truth value of sentences in logic, we should point out that so far we have been using only propositional logic. Propositional logic is sometimes also called the zeroth order logic. The key aspect of propositional logic is that it does not have any variables. So as an example, I may have a sentence which says, if the animal lays eggs and the animal flies, then the animal is a bird. And here I'm talking about a specific animal. But sometimes I might want to talk about animals in general, any animal, all animals. In that case, I would want to introduce variables in it. So in first order logic, also known as predicate calculus, I might want to say something like, if X lays eggs and X flies, then X is a bird, which has a form very similar to the form here, except that instead of animal, I now have a variable. Now, I have a variable here, but I must also specify the range of the variable. And what I really want to say here is for all animals. Therefore, I'll introduce a new quantifier over the variable X. This quantifier is called a universal quantifier. It is generated with this symbol. This is a symbol for a universal quantifier. And this says now for all X, if X lays eggs and X flies, it implies that X is a bird. One thing to note here is that I could have rewritten this sentence with a universal quantifier back into propositional logic by having lots of sentences like this in propositional logic. So I could have said lays eggs, animal 1, flies, animal 1, implies bird, animal 1, lays eggs, animal 2, and flies, animal 2, implies bird, animal 2, and so on and so forth for each and every animal that is possible. But by writing it in the form of a variable and universal quantifiers in it, I can reduce the number of sentences I have to write into just one sentence. So we have introduced variables, and we have talked at least about one quantifier so far, the universal quantifier, that applies for all values that that variable can take. Sometimes I might want to specify a different range of the variable. Not all values that the variable can take, but at least some values that the variable can take. So consider again this sentence. Here the animal is referring to a specific animal. Now let us look at the second sentence on the screen. And this sentence is the variable y. It says that if y lays eggs and y flies, then it implies that y is a bird. This sentence is a very similar form to the previous sentence except for the variable y. I can specify the value that the variable y can take. This time I want to specify not that this sentence is true for all values of y, for all animals, but supposing I want to say that it is true for some, at least one animal, in which case I'll use an existential quantifier. Here is a symbol for an existential quantifier. This existential quantifier says that there is at least one animal for which this sentence happens to be true. Okay, let us set aside predicate calculus and return back to propositional logic. Recall that we had found ways of writing sentences in propositional logic. We had found rules of inferences. We could prove theorems. We could find the truth value of new sentences. However, we found that those methods were computationally not very efficient. So AI has developed more efficient methods. One of those methods is called resolution theorem proving. Let us take an example to illustrate how resolution theorem proving works. So imagine there is a robot, and this robot is working on an assembly line. It's a factory robot. And on the assembly line are coming various kind of widgets. The robot's task is to pick up each widget as it comes on the assembly line and put it in a truck. However, there are some humans in this factory who play a joke on the robot once in a while. They glue the widget to the assembly line belt so that when the robot tries to move it, it cannot move it. But the robot is a smart robot. This is a logical agent. So when it cannot move it, it uses its logical reasoning to figure out that the box is not liftable. And the moment it knows that the box is not liftable, it lets go of the box. It moves on to the next one. Everyone got the story? All right. So let us suppose that the robot begins with some knowledge in its knowledge base. And this knowledge in its knowledge base that it begins with says that if cannot move, then it implies that not liftable. Now it tries to move the box, the next box on the widget. Its percepts tell it it cannot move. It needs to prove that it's not liftable. Now, of course, this is a trivial example. I'm sure you all understand it. You could potentially apply simply modus ponens to prove that it's not liftable. If P, then Q, P, therefore you can infer Q. But we'll use this example to show how resolution theorem proving works. So the first step in resolution theorem proving is to convert every sentence into a conjunctive normal form. A conjunctive normal form of a sentence can have one of three conditions. It can have a literal, that can be either a positive atom or a negative atom. It can have disjunctional literals, like here, can move or not liftable. Or it can have a conjunction of disjunctional literals. In this example, the third condition doesn't occur. So the first thing we must do is to take the first sentence. The negation of not move implies not liftable, and remove the implication because an implication cannot occur in conjunctive normal form. So the first thing we need to do is to rewrite this sentence, the first sentence, to remove the implication, because implication cannot occur in a conjunctive normal form. So now we use the implication elimination rewrite rule to rewrite this in the form of can move or not liftable. Remember, that was alpha implies beta becomes not alpha or beta. So the not of negation of can move becomes can move or not liftable. So we have done it for the first sentence. This is now in a conjunctive normal form. We can do the same thing for the second sentence, but wait, the second sentence already is in a conjunctive normal form. We don't have to do anything. Now the robot wants to prove that that box is not liftable. Resolution theorem proving is like proof by refutation. To do proof by refutation, we'll take the negation of what we want to prove. We wanted to prove not liftable. We'll take its negation, which makes it liftable. Okay, so now we got three sentences. This was the first sentence that the robot was bootstrapped with. We have just converted into a conjunctive normal form. This was the sentence that came from its percepts. It saw that the box cannot move. And this is the sentence, rather than negation of the sentence, the refutation of the sentence that it wants to prove. So we have three sentences now. The first sentence came from the bootstrapping of the robot's knowledge base. This is the axiom that the robot assumes to be true. The second sentence came from its percepts. The robot tried to move the box. It could not move it. The third sentence is coming from taking the negation of what the robot wants to prove. It wants to prove it's not liftable. So it's going to take the negation of it and then show that it's going to lead to a null condition that we'll view as a contradiction. In resolution theorem proving, we always begin with a literal in the sentence that we want to prove. So here that sentence is liftable. And we look for a sentence that contains the negation of a literal in this sentence that we want to prove. So the sentence here was liftable. Sentence S1 contains a literal, which is a negation of that. So we pick S1 and not S2. Note how efficient it was to decide which sentence in the knowledge base to go to. The sentence contained a negation of the literal. So liftable and not liftable cannot both be true. We know that. And therefore, we can eliminate them. This is called resolution. We resolve on liftable and we remove them from the sentences. Now, we were at sentence S1. That leaves us with can move. So now we pick a sentence that has the negation of the literal can move. Sentence S2 has a negation of that, and we can resolve on can move. They cannot both be true. When we resolve on both of them, those get eliminated as well. And now we see we've reached a null condition. This null condition represents a contradiction, and now we can infer that liftable cannot be true. Therefore, not liftable is true. The robot has proved not liftable. In this case, it appears as if resolution theorem proving is more complex as modus ponens. In general, it is not. It just appears here because this condition happened to fulfill the form of modus ponens directly. In general, deciding on which sentence to apply the modus ponens on and how to combine those rules of inferences turns out to be computationally harder than deciding how to apply resolution theorem proving. Let us make this example a little bit more complicated enough that it cannot be proven simply by applying one instance of modus ponens. Imagine that a robot proved to itself that this box is not liftable, and the humans in the factory who are trying to make fun of the robot said to the robot, well, the reason it's not liftable is not because it's not movable, but because your battery is not working. So now the situation is more complicated. The robot must also check its battery. So now the robot begins with slightly different knowledge in its knowledge base. So suppose that the knowledge in its knowledge base is cannot move and battery full means it's not liftable. It finds from its percepts again it cannot move. So it checks its battery and finds that the battery is full. So there are two new sentences that get written in the knowledge base. Now the knowledge base contains 3 sentences. As earlier in resolution theorem proving, the agent must convert all these sentences in its knowledge base into a conjunctive normal form. That means that the sentences can contain a literal or a disjunctional literals or a conjunction of disjunctional literals. So we begin by removing the implication from sentence 1 because an implication cannot occur in a conjunctive normal form. So when we remove implication from the first sentence, we get this sentence. But the sentence is not yet satisfactory. It is not yet a conjunctive normal form because this is a disjunction of conjunctions, and what we want are conjunctions of disjunctions. So we apply the De Morgan's law, and now we get the following sentence. We're simply taking the negation inside, which flips the conjunction into a disjunction, and now we have 3 literals connected with disjunctions, and this is a conjunctive normal form, disjunctional literals. So now we have in the knowledge base 3 sentences, all 3 of them in the conjunctive normal form, either literals or disjunctional literals. Recall that the robot wanted to prove not liftable. So it takes the negation of that. This is again proof by refutation. So it considers liftable. So now the knowledge base has 4 sentences. This 4th sentence is coming from the negation of what it wants to prove. Once again, the reasoning begins by the literal that it wants to prove, in this case liftable, and it finds a sentence in which the negation of the literal is true. So once again, we begin with the sentence S4 because that is what we want to prove. And we find a sentence in the knowledge base which contains a literal, which is a negation of the literal in the sentence S4 that we want to prove. We resolve on this because they both cannot be true, and resolution here simply means that we drop them. Now, in this sentence S1 that is under consideration currently, we have 2 literals. We can begin with either one of them. Let us begin with not battery full. We'll try to find a sentence which contains a negation of this particular literal. There is a sentence S3 which is a negation of this, so we'll resolve on this. Battery full and not battery full because they both cannot be true. We'll drop them. Now in sentence S1 we are left with just one literal, can move. We can try to find a sentence in the knowledge base which contains a negation of that literal. Here it is. And so we can resolve on them, and we resolve on them, we drop them, and once we drop them, then we have a null condition, which stands for a contradiction. So we reached a contradiction. Therefore, the assumption that this was liftable cannot be true. Therefore, not liftable is true. And we have just shown that resolution theorem proving, in this case, proves what the robot wanted to prove. One important point to note here is the issue of focus of attention. Often when the problem space is very complex, for example, when the number of sentences is very large, the sentences are very complex, it can become really hard for the logical agent to decide what to focus on. But because we have converted everything in a conjunctive normal form, and because resolution theorem proving is making use of resolution, therefore, at any particular time, the logical agent knows exactly what to focus on. You always begin with this literal. You always try to find a sentence which contains its negation. You always resolve on that. You take a remaining literal in the sentence and proceed forward. This focus of attention, this computational efficiency of resolution theorem proving is arising because of what are called horn clauses. A horn clause is a disjunction that contains at most one positive literal. This is happening in S1. This is a disjunction that contains at most one positive literal. This is a negative literal. This is a negative literal. And the fact that it contains just one positive literal is a very powerful idea because that's where the focus of attention comes from. Let us do an exercise together to make sure that we get resolution theorem proving. So consider this sentence: if an animal has wings and does not have fur, it is a bird. Write this sentence down in formal logic. You can use the predicates has wings, has fur, and bird. David, what did you write?
So starting at the beginning, has wings becomes the predicate has wings. We're doing a conjunction, so and. Does not have fur, so not has fur. Those two things imply that it's a bird.
That's good, David. Now let us put this in a form, in the conjunctive normal form that we can use in resolution theorem proving. So since an implication cannot occur in a conjunctive normal form, we must eliminate this implication. So please eliminate the implication from this sentence and rewrite it in this box. What did you get, David?
So this was a little bit more complicated. We know that from our earlier formula, if A implies B, then to rewrite it with implication elimination, we write not A or B. So or B is pretty straightforward, or bird. We take the not of the conjunction over here and say not has wings and not has fur. Now some of you may have jumped straight to writing this in full conjunctive normal form, but now we're going to move on and do that last step.
So this is not conjunctive normal form because we have a disjunction over a conjunction. What we want are either just disjunctions or conjunctions or disjunctions. So use De Morgan's law to write this in a conjunctive normal form. What did you have, David?
So with De Morgan's law, we take the negation on the outside and apply it individually to the predicates on the inside and flip the operator. So has wings becomes not has wings, not has fur becomes has fur, and the and becomes an or.
So imagine that the robot has this in its knowledge base and goes into a country where it finds an animal, and from its percept it knows that this animal has wings and it does not have fur. So these two additional sentences get written in the knowledge base. Now the robot wants to prove that this is a bird. In order to do resolution theorem proving, what should the robot begin by writing in this box? What should the S4 sentence be? What do you think, David?
So in resolution theorem proving, we always assume the opposite of what we're trying to prove. We're doing proof by refutation. So we're trying to prove that it is a bird, so we're going to assume it's not a bird.
That's right. Continuing further, so what part of S1 would we eliminate first? What do you think, David?
So in resolution theorem proving, we start with whatever it is we assumed and look for the negation of that in an earlier sentence. Here we find not bird and bird in S1. So we're going to resolve on not bird and bird and leave both of those out.
That's good. So what shall we do next? What shall we resolve on next? Of the four choices, which one did you pick, David?
So I picked the first one, but I think there's actually two correct answers. What we're looking for is something else in S1 that has a negation in another sentence. Not has wings has a negation in S2, so we could resolve on S2 with the not has wings portion of S1. Has fur also has a negation in S3, so we could also resolve on S3 and the has fur portion of S1.
This is right, David. At the end of this, we are left with null, which is a contradiction. Therefore, our assumption that it's not bird is false. Therefore, it must be a bird, and the robot has just proved that this must be a bird. Note what we have done. We have mechanized parts of logic. Instead of coming up with large truth tables, and instead of coming up with complex chains of inference based on modus ponens and modus tollens, we have found an algorithm called resolution theorem proving, which is an efficient way of proving sentences and their truth values. This is how it works. Take all the sentences in the knowledge base, convert them into conjunctive normal form. Take what you want to prove and its negation. Put that as a new sentence. Now, starting with this particular sentence, the new sentence, find a literal in another sentence on which you can resolve, and keep on doing it until you find a null condition, which is a contradiction. If you don't find a null condition, if you don't find a contradiction, that means that what you started with cannot be proved.
So how would you use formal logic to develop an agent that can solve Raven's progressive matrices? As with production systems, we can kind of face this at two different levels. One, you could use formal logic to represent the overall algorithm that the agent uses to solve any new problem. Or, secondly, the agent could use formal logic to develop its understanding of a new problem that just came in. It could then use those formal rules to develop the transformations that occur within the problem and transfer those transformations into the new answer. Alternatively, you could also use formal logic to allow your agent to prove why its answer to a particular problem is correct. Then, if the answer is actually incorrect, the agent may have the information necessary to go back and repair its reasoning and do better next time. So today we've talked about formal logic in order to set up a kind of formal language for us to reason with going forward. We started off by talking about formal notation, including conjunctions and disjunctions, so that we can write sentences in formal logic. We use that to then talk about truth tables and examine some of the properties that we need going forward, like De Morgan's law. Using that, we investigated some of the inferences that we can draw using formal logic. And finally, we looked at proof by refutation, which kind of capitalizes on everything we've talked about so far. Next time we'll be discussing planning, which leverages the formal logic that we've developed in this lesson. It allows agents to reason more formally about initial and goal states. Interestingly, planning actually has its history in the kinds of proofs we've developed here. Originally, agents would prove that a particular plan would work. So that's why we talk about formal logic before we talk about planning.
The connection between logic and human cognition is interesting. Logic is a very important school of thought in AI for several reasons. One reason is that logic provides a very formal and precise way of reasoning. Another reason is that logic provides a formal notation for expressing how intelligent agents reason, whether or not they are using logical reasoning. But does this mean that logic is also the basis of cognition? It certainly appears that humans use logic some of the time. For example, I may have a statement like, if I get a big bonus, I'll take a long vacation. I did get a big bonus, therefore I may infer I'll take a long vacation. This is clearly modus ponens. But simply because our behavior appears to be logical does not necessarily imply that we use logic as a fundamental reasoning strategy. I might solve a new problem by analogy to a previously encountered problem. I did not use logic, but my behavior appears to be logical. The logic that we have considered so far is deductive logic. But a lot of human reasoning is inductive or abductive in its character. If you haven't come across the term abductive so far, we'll discuss it in detail later in the class. Deduction has to do with reasoning from causes to effects. Abduction has to do with reasoning from effects to causes. When you go to a doctor, you go with certain signs and symptoms. Those are the effects. The doctor comes up with a disease category. That's the cause. Abduction is reasoning from data to an explanation to a disease category for that data. Induction is, given some relationship between cause and effect for a sample, how do we generalize it between a cause and effect relationship for a population? So while human reasoning appears to be inductive and abductive in character much of the time, the logic that we have considered so far is deductive. That's yet another issue that we'll return to later in the class.
All right, write what you learned in this lesson in this box right here.
Thank you for filling out this box. It helps us understand how the learning is going in the class.